Alright, what's up? It's Andy, and today we're just gonna breeze through some simple area integration problems using what we know about integration. If you recall from a couple of videos ago, I showed you that integration basically takes the area under a curve. You can think of it as an operation that produces like a million like infinitely small bars under a curve and then adds them up. So I'm going to show you how to integrate and get the area this video. So integration is basically the key operation here. But you'll notice that I've got two numbers here, a and b. And these numbers are called the bounds. And what they do is they say, well, we're trying to figure out the area from b to a. B is usually going to be the lower one, A is going to be the greater one. So A is going to be greater than B. So the way we calculate this is we take the indefinite integral of x squared, so we just normally integrate it. So that's just going to be x to the third over 3. If you remember integration, x n plus 1 over n plus 1. That's how you do it. But now, how to put in a and b? Well, we're going to sub in a for x, a to the third over 3. Then we're going to subtract we're going to subtract b subbed in for x over here. So it's going to end up being a to the third over 3 minus b to the third over 3. So you sub in a for the first one, you sub in b for the second one. I'll draw a little map. There we go. That's totally not confusing. Anyway, let's get on with it, and hopefully you'll learn it. So, right here, we got the integral from 0 to 4 of x squared dx. So it's basically the same as up here. I'm not really going to show you the step involved to calculate this because I just showed you it. And now we're going to plug in 4 for x. So that's going to be 4 cubed over 3 minus 0 cubed over 3. And these ones are awesome because the 0 just, he's out of the way. You don't have to worry about him. And you just get 4 cubed over 3. And let's see, that should be 64 over 3 if I'm not mistaken. Yeah, it's 64 over 3. Anyway, let's move on to a more complicated one. This sine x squared cosine x dx from 0 to pi over 2. You're probably thinking, whoa, that's a mouthful. I don't want to integrate this. But it's actually a lot easier than it appears because you can just use u substitution. And if you remember what that is, it's one of these is equal to u if you can say another part of the function is the derivative of this function over here. So in this case, u would be sine x, and du would be cosine x dx. And remember, this is reversing the chain rule. And so if we do this, we get u squared du, because we can sub in u or sine x for u, and du is equal to cosine x dx. You just sub that in and you get that. But you'll notice that I haven't done anything over here yet. And that's because if you're using u substitution, you can use a little neat trick to speed up the computation. Because, well, it's true that you could just leave these at pi over 2 and 0 and then just convert it back into a function of sine x at the end. It's actually a lot faster if you convert these to u values instead of x values. So the way we do this is we take this formula right here, and we're going to do u equal to sine of a, which is pi over 2. So sine of pi over 2 should be 1, so u is going to be equal to 1. That's the first one. And now we do u equal to sine of 0, which is just 0. And we just put in 0 right there. And so all of a sudden it becomes this. 1 to 0 of u squared. And
holy shit! We'll always love you! I can't believe you did this to me! God damn it! How could you do this to me?
Now we can just integrate like normal, u to the third over 3 from 1 to 0. I forgot to mention this. This means that you've already integrated the function. You've got the indefinite integral right here. But now you want to figure out the area in between. So you just, this function right here is equal to 1 cubed over 3 minus 0 cubed over 3. And that just equals 0, and you get 1/3. And it's another one of those zero problems where you can just get rid of it right off the bat. And now we got a little something more interesting. 1 over x dx.
Damn it. There are people out in the hall.
So, integral from 0 to 7 of 1 over x dx. Now, we can rewrite this as x to the negative first from 7 to 0 dx. And if we try to integrate this, we get x to the negative 1 plus 1 over negative 1 plus 1. But if we simplify this, we get x to the 0 over 0, and that's not a thing. So how do we integrate this? Well, this is actually Calc 2 material. I'm just speeding up a bit. But just remember that ln of x, or the natural log of x, has a derivative, and that's 1 over x. Conversely, integrating 1 over x gives you ln of x. So just remember that the integral of this should be ln of x. So now we got ln of x is our integral, and now we're going to integrate it from 7 to 0. I'm just going to move that stuff over. That's very important if you move on to Calc 2 that you know your functions. There's a couple more like arctan. I think you need to remember, I'm pretty sure you need to remember secant at some point, but you can also use integration by parts for that. So ln of x from 7 to 0. Well, ln of 7 minus ln of 0. And I don't really want to whip out my calculator and calculate that, so I just know that this equals 1, ln of 0 equals 1. So it's just ln of 7 minus 1 for that one. That's the area under that. And now we got a slightly more complicated one, which looks like quite a lot of fun, if fun means torture, but it's really not too bad. So right off the bat, we can see, well, that one's higher. That one has a higher exponent than this one out here. So we're already thinking, oh, we could definitely use u substitution, because if we set u equal to 4x to the third minus 3, du is going to be equal to 12x squared. That's not a 12 out there, but we can just simply put a 1/12 over here. 1 over 12 du, and set it equal to x squared dx. And so the way we're going to rewrite this function in terms of u is 1 over 12 out here. Whenever you have a constant multiplier in here, you can just shift it out there. It doesn't change the integral at all. And okay, now we're going to set it equal to u, so that would be u du. Yep, that's correct. And now we're going to try and find the bounds, which might seem a little bit difficult. 4 times 13 to the third minus 3, and then 4 times 4 to the third minus 3. And those are pretty big, so I think I'll just leave them like that. I might even go back and change it into terms of x later on, because in this case, that would seem to be the best way to figure out the area of this function. So 13 cubed minus 3, 4 to the 4 to the third minus 3. Okay, and now we just integrate this, so that's just going to be u squared over 2. And now we multiply the 12 back in, so that's going to end up being u squared over 24. And these bounds again for And what you can do, typically, on most systems, like if you're doing homework online, sometimes they take this. So you can just, you can just plug it in, like 4 times 13 cubed minus 3 squared over 24 minus 4 times 4 to the third minus 3 squared over 24. Give me a second and I'll figure out the actual value. Okay guys, so I was just using Wolfram Alpha to check my work, which is something that you should do. Make sure that you're not cheating directly off of Wolfram Alpha, which, I'm not sponsored by them or anything. It can handle most complex operations like this, but don't cheat off it, do your work. Just make sure that, if you're unsure of something, you do it first, and then you can go on Wolfram Alpha to check. And sometimes Wolfram Alpha will be wrong, so just use your common sense. Anyway, the answer to this is 3,213,009, which is quite large, but typically, if you're doing homework online, like you probably will be doing in college, you can leave it like this. They will not, well, I can't say for sure, but typically they won't ask you to calculate something that big. Anyway, that's all I got for you today. It's Andy. Peace out. Don't cheat. Bye.